Okay, now let's get set up from current slide. Okay, can you see my screen that says ore minerals? Yay or nay? Anybody? Okay, it said I could, but I just wanted to make sure. Okay, now this was a slide that I could not find position where it's located exactly in the text. Again, the slide set is from a slightly older edition from the edition that we're using. They didn't send me a slide set for the current edition. So I think we went through everything on this slide and we're ready to start the next one. Any questions or issues before we move on? All right. Okay. We've already done this too, haven't we? Aren't we on metamorphic rocks right now? In fact, we're past this. So evidently, sorry about this. We went through sedimentary rocks, lithification. We started on metamorphic rocks. We did this slide here. Here is where we're picking up. I'm sorry. Here's the slide we're starting with today. Whoa, here comes somebody else and it's blocking the name. I don't know if you can see it or not. Let me see if I can see who it is. Harry, I think, is coming in. And then two more people are waiting. Thomas. So Harry and Thomas are on the way. Harry's here. And Thomas is here. Are trying to, oh, Roy must have left and come back. Let me get him back here. I see Harry now. Okay. And Roy was already here. But he must be having trouble. All right, I hope Roy's back now. So let's see what we're up to. 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay. All right. Where are you located? Oh, wow. Okay. So we probably got a little bit of time before it makes its way here, so we'll see. Yeah, today seems like a sort of unstable day, so stand by. I guess that could be affecting any of us. All right. All right. Now, like I was saying before, my slide had us on the wrong place. Here's where we're picking up this time. Classification of metamorphic rock. Someone remind me, what in the world is a metamorphic rock? One that has undergone, yes. Absolutely. Okay, you just hit, I think, at least two of the three, maybe all three of them. Any rock that under a lot of pressure, generally a lot of heat, which usually comes with pressure, and over a long period of time may change its actual crystal structures of the rock, of the minerals that are in there, and therefore if it's been changed, it metamorphosized. Right? I think that's a word. I don't know about you, but I remember where I first learned the word metamorphic was in relationship with the caterpillar to a butterfly. That was the process of metamorphosis that I first learned. A completely different animal, it looks like, yet it all came from the same source. It went into its cocoon as a ugly fuzzy little caterpillar and came out as a beautiful light butterfly. Okay, complete change, but using exactly the same materials. Well, that's what a metamorphic rock is. It was either an igneous rock that metamorphosized to be a metamorphic rock. It could have been a sedimentary rock changing under pressure, temperature, and time to become a metamorphic rock. Or it could have been a former metamorphic rock changing into another one. Okay? And we saw that in the last table that we did, which was this one. It won't go back, so I have to, this is so bizarre, I have to click on the screen before it'll go back. There, we saw lots of different kinds. Whoops, here's Valerie. Good deal. I wondered where she was. Valerie's here. She's usually here waiting for me to end my previous class, but today she was a little bit later. Okay, so here we have a clastic sedimentary rock going into a metamorphic, going into a different metamorphic, going into a different metamorphic before it finally becomes igneous again. Here was a chemical sedimentary rock going into a metamorphic before it melts again and becomes igneous again. Here's another clastic metamorphic rock going into clastic sedimentary rock going into a metamorphic rock before it melts and becomes and here's Caitlin coming in. So maybe I should have held off a little bit longer. Caitlin's coming in. There she is. Okay. And finally, we had even an igneous rock going into a metamorphic rock that looks a lot like a metamorphic rock that came from another metamorphic rock, which came from a sedimentary rock. But this became a schist, became another metamorphic rock, and then melted and went back to being igneous. Okay, so yeah, any rock that has undergone pressure, temperature, time, Harry hit it right on the nose to become, and I can't get it to advance until I click on the screen again. Okay, here we go. So how do we classify these metamorphic rocks? We knew how to classify igneous rocks. They were extrusive or intrusive, depending on whether they solidified outside the earth or inside the earth. They were fine grained or coarse grained, depending on the time over which the grains, the crystals formed. We did sedimentary rock as clastic or chemical, and then even among those we had other classifications. Well, how do we classify metamorphic rock? Well, one way is by the degree of foliation. Now, does anyone know what the term foliation, where that comes from? I'm looking out of my window now and I see some foliage. What foliage might I see? Leaves on the tree. You're absolutely right. So anything that stacks or lines up as flat plates, leaves, like a leaf on a book is a page in a book. Okay? Anything that lines up like that is foliated. If it's not lined up like that, it's non-foliated. So foliation is the alignment of flat crystals, flakes, into sheets. And sometimes this metamorphic process compresses crystals into flat sheets. Let's go back and take a look. Remember, shale was a sedimentary rock that's already in layers, and the metamorphosis smashes them together and forms really, really strong slate plates, you might say. That's a highly foliated rock. But then more pressure comes along and schist is coarsely foliated. And when it finally gets to gneiss, it's hardly foliated at all. Remember, that's the one that was all wrinkled and garbled and stuffed together. That was gneiss, not foliated much at all. Limestone generally isn't foliated to begin with, so marble generally isn't foliated later. Sandstone may be, and the quartzite may be, and again, the schist, igneous rock, fine-grained igneous rock, could become coarsely foliated but then non-foliated, depending on the metamorphosis processes. So the alignment of flat crystals, flakes into sheets are caused by pressure on the parent rocks, and that pressure If it builds and keeps it into sheets, then the rock cleaves along planes between the aligned grains. Okay? Isn't really saying a lot. However, non-foliated, the parent rocks consist mostly of one mineral, and the grains are not aligned in the sheets. They just become harder, tougher, but still three-dimensional grains, non-foliated. So here's how we separate some of those. The non-foliated would be things like quartzite and marble, which I mentioned before. The quartzite here, sandstone itself can be somewhat foliated, but when it becomes quartzite, quartzite is a three-dimensional crystal, not foliated into two dimensions. Limestone generally is a bulk type rock, and it forms a bulk type non-foliated marble. Okay? Whereas very fine foliated, that would be like, whoops, here comes one. Good deal. Okay? Oh, let me let them in. I'm marking them in the book, but I'm not letting them in. Okay, there we go. There's one. Okay. There's another one. No, I'm just kidding. Okay. All right. So slate would be very finely foliated because it really is easy to break into sheets. Remember that piece of slate I brought up here? That was used in roofing materials in New Orleans at one time. Okay? That was finely foliated. That very finely foliated. Schist is just finely foliated, and gneiss, I was saying, is mostly unfoliated. It's coarsely foliated. So we go back here to the table here. I can't get it to go back until I hit the screen again, and now it'll go back. Okay. Shale is basically comes in layers, making very finely foliated slate. More pressure crunches some of those together, and you get finely foliated schist. But then over time, more pressure, more heat warps it some, and you get coarsely foliated gneiss. And then granite, of course, is not foliated because it goes back to igneous. Limestone, not at all two-dimensional to begin with, so marble, non-foliated. Sandstone, kind of the same way, non-foliated quartzite. This igneous fine-grained rock will be slightly foliated maybe to start with, but schist is finely foliated, nice, coarsely foliated, and then when it melts and goes back to granite, of course, it loses its foliation. So there we saw how the foliation, that's how we classify metamorphic rock. And that pretty much finishes page 451. I can't remember if I mentioned to you, I think we did, Victor Moritz Goldschmidt. Okay? He was born in Switzerland, but at some point moved to Norway and did most of his really impressive scientific work in Norway. So he was basically the father of geochemistry, okay, the founder of modern geochemistry, which is sort of what we've been talking about. Okay, the table we just saw, this one here, 17.5, is on page 452 of the big book, which would be 1717 if you have a smaller book. Oops, here comes Capri. Okay, let me get her here. All right, turning into a good size class today. It started off a little slowly, but now it's building up. Okay. But this table 17.5 is on the top of my page 452, probably your page 1717. And there it is. And then a couple of figures under that. Let's see if they show them here. Again, it won't advance until I click on the screen, and now it will advance. And these are a couple of pieces of, and there's that same table we just saw. It's listed here as figure tables. I'm sorry. That was 1719 in our book, 1720 in the old book. Same thing we saw. Here is a piece of marble. They show another sample of marble on page 452 or 1717. Slightly different looking piece of marble, non-foliated. Okay, but this nice rock is very coarsely foliated. Those are not very pretty sheets, but they can be divided into very coarse sheets. Not very flat sheets, but coarse sheets. Okay, and that was that picture of one of the oldest pieces of rock that people have found anywhere on Earth. That banded metamorphic rock, very old, at an age of 3.8 billion years, probably among the oldest rocks on the surface of the Earth. Okay. In our current text, there is a different picture of it, just a portion of that rock, showing some of that really coarsely foliated material. Okay. Any questions on metamorphic rock? Okay. Let's move on. By the way, this piece of marble, if you haven't figured it out, that's a penny there, so it just gives you the relative size of that piece of marble. No foliation at all visible there, non-foliated. So now we move into 17.5, which is the rock cycle. Okay? Get used to this concept. Nothing ever stays the same. Now, it seems like it does, but it really doesn't. Everything is always changing. Now, the rock cycle may take hundreds, thousands, or millions, maybe even billions of years to change, to transform, but they're constantly happening. Okay? Rocks are transformed into new types by the Earth's interior and exterior dynamical processes, meaning moving. These are, and I thought we hit a slide, excuse me just a second, I got a sneeze. Sorry, I didn't get the microphone moved in time. I'm going to turn off the ceiling fan. Up till now, I had been hot in here just about my whole last class, but like I think Roy was saying, the weather seems to be changing, and changing fairly quickly, and it seems like we've had a temperature drop, though I don't see any rain or anything to cause it, but something's changed anyway. So anyway, rocks are changing into new type by these processes. Moving continents, certainly if you got continents moving, there's a lot of pressure. Could be a lot of heat. Lots of things going on. Seas advance and retreat. Whoa, what is that all about? Now this again is talking geologic time, which is long periods of time. Well, at one time, the Atlantic Ocean came up to probably within a few miles of where I lived when I grew up in Georgia, because there on the Savannah River there was an area called Shell Bluff, and there was a bluff filled with seashells, and yet it was probably 100 miles from the Atlantic Ocean. At one time the Atlantic Ocean was up that high, and other times it's retreated back. Seas advance and retreat. That creates new pressures, new minerals, new materials. Things are always a-changing. Even old established rock, and we'll talk about this in a couple chapters from now, they are weathered and then eroded. Weathered means they're broken down into smaller pieces, and eroded means carried off and carried somewhere else. That can be weathered and eroded by either wind or by rain. Wind and water are your big eroders, and water is by far the biggest eroder and weatherer, okay? Though wind can do some definite damage as well. Where do you think those particles from sedimentary rock came from? They came from weathered and eroded pieces of other rock. They could have been igneous rock, they could have been other sedimentary rock, they could have been metamorphic rock, but those pieces got back together and then started the process of lithification all over again and became sedimentary rock. Later maybe to become metamorphic rock, maybe later to go back to being igneous rock. Nothing ever stays the same. May stay the same for a very long period of time, but never stays the same. This is one of the most interesting little graphs I think I've ever seen, and it really shows it well. Now, if you recall, all rock was at one time igneous rock, because at one time everything on the earth was molten. Everything in the earth was molten. That was back when we were just forming as a planet, the protoplanet stage. The earth, the sun had just been through all these nuclear explosions, throwing materials out there, very hot materials. They coagulated, and formed the planets and the other areas. So all rock was at one time igneous rock. When that magma cooled from whatever billions of years ago to hundreds of years ago or last year, if magma cooled, it became igneous rock. Okay? Now remember, we're going to talk about later weathering and erosion that will break up igneous rock and then maybe make sediments, little pieces of rock that become sedimentary rock. Okay? That's down here. Or that igneous rock could undergo, as I don't remember if it was Roy or Jacob or Harry, Harry I guess it was, saying under a lot of pressure and temperature and time, that igneous rock could change into metamorphic rock. Okay? So, let's go back to the sedimentary rock. It picked up from sediments. Now those sediments may have been igneous sediments that broke apart. It could have been metamorphic rocks that broke apart by weathering or erosion. It could have been other sedimentary. Whoops, here's Cormetia. I think she was already here once, so I'm not going to count her but once, but let's just see. Cormetia, did I have her here? Yes, I did. Okay. Who is this? Capri, yeah, I got you. I guess it was before you could hear me, but I saw you were coming in. Okay? Alrighty. And as someone commented earlier, I've got on a headset now and microphone here, so I can turn my head to my heart's content, and y'all should still be able to hear me. Okay. But even former sedimentary rock could break apart again, become new sediment, and the lithification process is where first you get compaction and then you get cementation. Okay? As those sediments then turn into rock again and they become sedimentary rock. And those sedimentary rock, under more heat, more pressure, and more time through metamorphism, could become metamorphic rock. Okay? Or they break down and become more sedimentary. But all rock, after a while, if it gets buried deeper and deeper and deeper, more heat, more temperature, more pressure, at some point it's going to melt again. As soon as it melts, it becomes magma again, and when that resolidifies, it's no longer metamorphic, sedimentary, or anything else. It's back to being igneous rock. That's the rock cycle, with many little subcycles. Okay, they can go around and around and around and around. So a rock during its lifetime, if rocks could talk, boy, it'd be interesting to hear what they once were, what part of what they once were. Okay. And if I can get this slideshow to move, that is the last slide in the section. Okay, in the chapter. All right. I say this every chapter, and I truly, truly, from the bottom of my heart, mean it. Nothing replaces reading the chapter. Okay? It's better to read it before I talk about it, and then maybe when you're reading it, because this is my experience as an undergraduate. I would go home sometimes and try to do this, especially true in math, calculus homework. Sometimes I could read that stuff we were going to do the next day, And I thought, what in the world are these words even saying? They're just calling words. But the next day in class, when the professor started talking about them, then I had at least read the words before, and they made a little bit of sense, and he helped me put them together. Those days I didn't read the material before class, when he was up there talking, it was just like it was when I was reading it the first time. Made no sense. Going back and rereading or going back and studying for the test, then say, oh, this is what he was saying. So the more you can expose your mind and the concepts to your mind, then the next time you hear it, the next time you deal something with it, you get more of your synapses making links, and it's making more sense. So please read the chapter. Okay? Once you've read it, the summary is maybe a little bit shorter than some summaries, a lot of italicized words, because you have a lot of terms here. The key terms are a bit shorter than normal too, but applying the concepts, well, that's a few shorter than normal too. Only 43 multiple choice questions, but they are the best questions to study for your test. If you know those, you're probably going to have most of the concept of the test down well. The answers are given after the end of those 43 questions. Then questions for thought. This is a few more than normal. There's 19 of those, and then 4 they call for further analysis. Okay, that's about normal, maybe a few shorter than normal. There's an invitation to inquiry talking about building rocks, and you can read that if you'd like. And then a parallel exercises. These are, to me, not as important, but if you're into that type of thing, these are a lot like the examples that are given in the book. There's a Group A and Group B. If you had the big book, Group A answers for those parallel exercises are in the back. If you don't have the big book, you probably can't find them, so it's up to you whether you want to do those or not. All right, now, got a little bit of an apology coming here. I've got your lab ready, but I didn't have time at the end of last week to get it onto PDF, into PDF format. Okay, so that means today, when it's time to start the lab, we're going to have a little break. I'm going to have to run downstairs and take pictures with our iPad, get it in the PDF format, get it back up here. Well, I have to email it to myself, get it back up here, fiddle with it a little bit, and get it so I can post it for you to do the lab today. It shouldn't take too long, but there will be a break right at let's see what time, 4:30. Okay, at 4:30 is when, is that right? Yeah, we go to, no, 4:15. We go to 6:15. So right at 4:15, I'll stop wherever we are and go down, make the, I'll check and make sure I have it done. I don't think I've done it, but I'll go down and make the PDF format of the lab and send it, and then I'll come back up, post it to Blackboard, and then we'll start working through the lab. Okay, sorry I didn't get it done. I was going to do it this morning, and the dean and the registrar called a special training session for department chairs, which I'm one, to be introduced to this new, I guess you call it a management package that we're going. Ever since we merged with Lawson back in 2005, I think it was, we've been on this old program called Alliant. It was a boondoggle done by a previous chancellor who had friends, and he got I don't know what the deal was. It worked okay, but it's archaic. It was poor. They've gotten several new chancellors since then, but this latest one has decided everybody in the system needs to go to a new thing. It's going to be called Banner. And if any of you are here in the fall, you will be exposed to Banner. Now, hopefully that exposure won't be too great and it won't cause you too much pain, but it's causing all the administrators a lot of pain right now, and will be causing us department chairs and instructors a bit of pain as we get used to it. Hopefully it'll be fairly painless for students, but you'll notice the difference. One thing, for instance, how many of you have been here for, say, more than a year? You probably know your ID numbers, right? When we go to Banner, you're going to have brand new ID numbers. In fact, they're not even called ID numbers anymore. They're called A numbers. And they couldn't use the same A numbers that you had before. Yeah, it's going to be brand new. So if you're going to be here in the fall, get ready for at least a few new things. Well, that was the training I was being exposed to this morning, and that ate up most of my 2.5 hours that I had. I was planning to get ready for lab today. Couldn't do it because I had to go through that training. Okay, so anyway, that's why we'll have a little bit of a pause in between what we're doing now and what we'll be doing then. So I'm going to end the, yes. No, every test that you have is a middle of the term. It's not a middle of the term. It's just an in the middle of the term test. Okay, so no, there is no separate midterm exam. There's all your regular tests and then the final exam. And the final exam counts the same as a regular test. It will be comprehensive. The one other difference is it cannot be dropped. You can drop your lowest test score if it helps your average of the chapter test, but the final exam can't be dropped. But no, I saw no reason to test you on each chapter and then do a midterm and then test you on each chapter and then do a final. That's just taking up extra time testing. So we're just having the chapter test and then the final. And we got enough of them. Okay? Absolutely. Get them in to me whenever you can. Okay? Because, yeah. Okay. Okay. I'm barely able to hear you. Could you say that one more time? I heard something about your student accounts and Blackboard and stuff, but okay, remind you of what again? I'm not. Oh, where to find it? Oh, okay. All of your tests and all of your labs so far have been on Blackboard Message. Okay, when you go to Blackboard, in fact, when we go there today, I'll show you exactly where that is. Can you wait till then, or do you want to see it now? What? Wait till then? Okay, yeah. I'll go step by step as much as Zoom will allow me. And to just let Roy know, it's getting very dark here. So, are you still? What's that? What'd you say? Roy, could you repeat? Or whoever said the last? Okay. Yeah, it's getting dark here. I think we're about to storm. Okay. But anyway, let me end the slideshow here and end it here, and we'll pick up. It says screen sharing is stopped. I realize that. We're going to pick up with chapter 18. This time went much better than my last class. It didn't disappear, but I do have to move these taskbars out of the way again, or at least one. Okay, my signal strength has reduced some too, so it may be due to weather. I don't know. All right, let's go from current slide. All right, chapter 18. Okay. Last chapter we just introduced what in the world are your rocks and minerals. and we talked about some of the things that made them change and adjust and transform and stuff was by pressures of moving stuff. Well, guess what? This chapter is focusing on those moving plates. We call that plate tectonics. So the very things we were talking about last time that were some of your driving forces and the reason stuff happened, now we're going to see what those forces are. Here's the core concept. This is on my page 458 in the text, your page 18-1, maybe if you have one of those small books. Earth has an internal structure, okay, and it cycles materials between the surface and the interior. Surface to interior, interior to surface, surface to interior. Just like we talked about before, the rock cycle, here we have materials being cycled. Now, this figure that you see here probably won't make a lot of sense to you right now, but by the end of the chapter, hopefully it'll make a lot more sense. These are some of the larger plates that make up the surface of the earth and the subsurface of the earth too. Okay, I'll just mention some of them. Here, if I could get there's my cursor, is the one we live on called the North American plate. It goes across here in much of all of Alaska, and here's a boundary for it, the Aleutian Island chain. We'll talk about that. And they actually draw it as if part of eastern Siberia is on the North American plate. Okay, now I don't see why and how that would be the case, but that's how they've drawn it here. Okay, and since we mentioned that, this is the Eurasian plate. Now Asia is the largest continent, and much of Asia is in this, but almost all of Europe is in that plate as well. That's why it's called Eurasian plate. Not all of Asia is in it. This part here, India, believe it or not, is on the same plate with Australia. So they call that the Indian-Australian plate down here. Here's another little bit of what we call Asia now. And this is the Arabian plate. And then there's the Dead Sea here. There's the Persian Gulf here. That separates this. That's a pretty small plate. Your African plate is down here. Your South American plate here. And you see the Eurasian carries over to here. And the African plate here. Notice here the Eurasian plate and the North American plate pretty much meet in the middle of the Atlantic Ocean. We'll talk about why that's true. And the African plate and the South American plate also meet pretty much in the middle of the Atlantic Ocean. And you see that meeting place is called the Mid-Atlantic Ridge. We'll talk about that later. There's another plate down here they don't name. I don't know what that is. But then the blue plate down here, now it looks awfully big, but that's because you've taken the covering of a sphere and spread it into a sheet, and that makes the parts down here stretch out way too big. The Antarctic plate is down here. It's not nearly as big as it looks like here. But here's some other really interesting plates. Here's Pacific plate here, and the Pacific Ocean is huge, but not all the Pacific Ocean is on the plate. Here are several island chains here that break up the Indian Austrian plates and the Pacific plate. Here's another plate here, the Philippine plate. The Philippine Islands are just about the only country in that. There's a tiny little plate over here called the Juan de Fuca plate. Okay, and then the Nazca plate down here is a really interesting one. And you'll notice a lot of times the boundaries of this are either mountains, island chains, and there's a reason for that. We'll talk all this before the chapter's through. So this, I think you'll find, is a pretty interesting chapter. Okay? So let's start with 18.1, which is a history of the Earth's interior. Now, we think the Earth was formed about 4.6 billion years ago when we were part of that solar nebula. The Sun, remember, came into being about 5 billion years ago. So after the Sun finished all of its explosions and things like this, throwing things out here into what now is the solar system, and it has already become a star, the Earth and the other planets finally cooled enough and started forming enough about 400 million years after the Sun got established. They finally settled out and became planets. About 4.6 billion years in the solar nebula, that massive stuff that was around the Sun. The early Earth, back in those days, was completely liquid, molten surface. Okay, part of that, it just got blown out of the Sun from enormously powerful nuclear reactions. Okay, that's going to keep things pretty liquefied. But also, all sorts of things were flying around in the atmosphere, so it was constantly being bombarded, and every time a collision happened, there was more heat given off. Okay, so it was a molten surface from the bombarding materials. That was about 4.6 billion years ago. The surface slowly cooled and crystallized. And what does molten material crystallize to? Good old igneous rocks. Okay? That's why all rocks were at one time igneous rocks, because we were all a molten planet, so everything was igneous then. But then the rock cycle started over billions of years, and things have changed a lot. Now, remember, we had a lot of radioactive material out there to begin with, so heat accumulated from the radioactive decay led to a second melting, this time of the interior. Okay, the interior of the Earth, at one time mostly the surface was molten, now the interior is molten, okay, as well. Now, that melting occurred in pockets, not throughout the interior. So there were some regions that were totally melted, some regions that were somewhat solid, some regions that were sort of in between. This led to the concept of differentiation. The melting and the gravitational effect settled out the heavier elements. They went toward the center of the Earth. The center of the Earth is mostly made up of iron, nickel, strangely enough magnesium, which isn't that heavy. But these heavier materials settled out interior, and that gave the Earth its present stratified structure. Now we're going to talk about that in a couple of future slides, so hold on to the concept. Now, the Earth has two cores. The very innermost core is solid again, and that's mostly because there's so much pressure on it, it's forced it to be a solid. Now we don't know much about it, we just know it is a solid, and we'll talk about that later of how we know that. No one's been down there. Journey to the Center of the Earth was a fictitious movie. It was science fiction, more fiction than science, okay? Nothing can go make a journey to the center of the Earth without being fried completely, molten completely, okay? So we don't know. We can only suppose and surmise. And by the way, Roy, it is raining like crazy here. The wind's blowing like crazy. Oh, and David Whitlock must have gotten kicked out and now is back in. So I've already got David here, I'm pretty sure. Yeah, David's still here. Okay, so I wouldn't be surprised if some of you get kicked out. If it's happening other places, I hope I don't get kicked out, because that would be really disastrous. Okay, so the outer core, the inner core, has become solidified, mostly due to pressure, but the outer core is still molten. And that outer core, as is the inner core, is mostly iron. Okay? Though it does have a fair amount of nickel and other things in it, but mostly iron. What are the conditions at the Earth's center? Unbelievably harsh. The pressure down there is about like 3.5 million, 3.5 million atmospheres of pressure. Okay, we talked about this, I think, before, didn't we? One atmosphere of pressure is about close to 15 pounds, 14.7 pounds per square inch. That's how you measure pressure. Force per unit area. Pound is a force measurement, a square inch is a surface measurement. Your two thumb joints together make about 1 square inch. Okay? And think how many of those square inches cover your body. Okay? An awful lot. Multiply that by close to 15, 14.7, that's how much weight you have on your body. You would be astounded if you knew how many square inches you have on your body. Multiply that by 15 pounds, and that's how much weight you have on you. Why doesn't it crush us? Because we are also pressurized. When you have a cut or a nick, the blood flows out. It doesn't flow in. It doesn't suck air in. That's because you're under more pressure than the atmosphere outside of you is under. Okay? So you are also a pressurized being. Okay? Now, we wouldn't be able to stand it on the surface of Jupiter if Jupiter had a surface, whereas on the moon, we would make it fine, but if we stayed there very long, we wouldn't be able to return to Earth very easily because most of our muscles would have atrophied because we would get used to almost no pressure on us. There is some, but not as much as on Earth. So yeah, we're under, but at the center of the Earth, whatever pressure you have here at the surface, 3.5 million times that much pressure would be at the center of the Earth. I think I told you before, every 10 meters of water adds another atmosphere of pressure. Now 10 meters would be about like a 3-story building. Our house is a 2-story building. You would have to include the attic and the very tip of our roof to be 3 stories. That deep in water, you're under a second atmosphere of pressure, one from the atmosphere above and one from that much more. And then as you keep going down, you have everything above you is adding to the pressure. So certainly at the center, you have a lot of what they call overburden. Everything's pressing down on you, 3.5 million atmospheres. No one's going to go to the center of the Earth. The atmosphere, the pressure would crush you in an instant. The temperature, though, would bake you. 6,000 degrees Celsius. Whereas you think boiling water is at 100 degrees Celsius. That's boiling water. You couldn't stand that. 6,000, that's 60 times hotter, you might say, than boiling water. That would be the temperature at the center of the Earth. Nowhere close to high enough for fusion to be started, but definitely hot. Okay? So those are the conditions at the Earth's center. Won't advance until I click on the slide. I don't know why. Okay, here we go. Now, how do we know that? How do we know anything of what I just said? If you can't go down there and measure it, how do we know? Well, here's a few ways that give, each of these is giving a different perspective of hints of why it's true. One reason is that Earth has a magnetic field. You say, wait a minute, what does that have to do with how the Earth is structured? Well, here's why. The only way a magnetic field exists is if you have moving charges. Moving charges create magnetic fields. Well, what charges are we talking about moving? Picture this. The Earth I'm not counting the oceans. The oceans are little puddles on the Earth's crust. So they're big puddles, but they're compared to the size of the Earth, they're very little puddles. Everything beneath the oceans and everything we know on the surface is solid, okay? And that solid sphere is turning, remember, really, really rapidly. Remember, we talked about this in an earlier chapter. Really twisting very fast. But remember that outer core is liquid, so that solid material is twisting around the liquid core, and the core is just sort of swirling around some. Well, that means there's constant friction between the outer crust, it's actually more than the crust, the mantle we'll talk about later, and the liquid outer core, and it's not a really smooth surface either. It's a very irregular surface. There are places where there's pockets of liquid, places where the solid pokes down into the liquid, and the solid is turning like this, and the liquid's being stirred by the solid. That's what's knocking charges off some of those iron molecules. And when those electrons get knocked off and are twisted around, that's what creates, a magnetic field. Sorry. I'm going to have to sorry, I've talked too long today and I'm losing my voice. That creates a magnetic field. So the fact that a magnetic field exists indicates somewhere down there there's enough friction to knock electrons off of a solid, so they're floating in liquid, and it has to be moving. Yep, that would account for the fact that there's solid liquid interface somewhere down there. And when I say liquid, I'm not talking about water, I'm talking about molten rock. Okay. Number 2, gravity effects. Okay, well, wait, what do you mean there? Gravity depends on the mass of the body. And no one can put the Earth on a scale and see how much we weigh, but we can basically deduce what our weight is, how heavy we are, how much mass we have, by how strong our gravitational field is. And we have the strongest gravitational field of any of the terrestrial planets: Mercury, Venus, Earth, and Mars. We have the largest. So that means we are pretty dense, okay? In fact, we're the densest of all the planets. Of all 8 planets, we are the very densest ones, okay? Because we know our gravitational effects and we know our volumes, and those go together to give you in a sense, how strong your gravitational effects are. Now, next issue, heat flow. People have studied heat flow through various materials. Oh, here's Scott coming in. Good deal. Let me get Scott on the books. Okay. There's Scott. Okay, got Scott here. Okay. They can measure and quantify how heat is flowing through those various materials. And they know that there are boundaries there which the heat flows through in different ways, meaning that there are different materials. The stratification, the internal structure, they can hypothesize what materials would be causing those changes in the heat flow. Okay? Now, here's ones that I don't know if you would have thought of being a good clue by how our internal structure is. Vibrations in the earth. What are we talking about there? Seismic waves. These are the waves that radiate outward every time you have an earthquake. Also, every time that someone blows up a nuclear weapon, you create this very weak read like an earthquake, but it still is readable on seismographs. So nobody can hide. If anyone's doing any nuclear testing, everybody knows, because everyone, that's an international agreement to share the data on earthquakes, okay, and that also shares it on nuclear explosions. Okay, so we're going to really be focusing on that feature, the seismic waves. They tell us an incredible amount of information about the structure of the Earth's internal structure. I seem to have lost my clip. I'll try to keep this my headset thing clipped on so it won't be dragging as heavily on me. Okay, so let's see how these go together. And again, I can't advance the slide until I click on it and then advance. Okay, let's look at those seismic waves. And by the way, we are in 18.2, Earth's internal structure. Actually, it began that slide, okay, and we're continuing it here. All right, there are three types of seismic waves, okay, and some of them have multiple names. So, and we'll talk about those, and hopefully the multiple names will not be confusing. They'll help reinforce what they are. The first type of seismic wave is the P wave. P wave, the letter P. Why the letter P? Well, you can think of it as two different reasons, and these hopefully will get together. The first of these is a pressure wave. It's a longitudinal, that may not make any sense to you, compressional or pressure wave. So the P you could think of as a pressure wave. Now, let me give you an example of a pressure wave. You've been listening to it all day long. Hold your hand in front of your mouth when you're speaking, and you'll feel little pulses hitting your hand. Those are pulses of air. That's what sound is. Sound is a pressure wave. Now, sound is not a seismic wave, so don't get me confused there. Don't confuse what I'm saying there. It's just an example of a pressure wave. It's a longitudinal wave, and what that means is the wave goes in the same direction as the particles. Those particles leave my larynx, voice box, and that's what creates the sound. And those waves leave and they go back and forth like this as they're going. Compression, rarefaction, compression, rarefaction. That makes its way to your ears, and your very sensitive little eardrums vibrate, and the other parts of your inner ear vibrate when they get touched by those tiny, minute little pressure waves, and that's what enables you to hear. Okay? So there's pressure wave or longitudinal waves, P waves. The other thing that P stands for is primary. They're the fastest waves. They're the first wave to get to you. Primary waves. So pressure wave, primary wave, longitudinal wave, these are the fastest waves to move. Now, pressure waves move through solid materials like rocks. They move through liquid materials like magma. They move through liquid materials like oceans. You know, they go through any type of material, solid, liquid, or gas. Pressure waves. Okay, I'm sorry, I'm going to have to my throat is almost feeling raw now. I've talked so much. Okay, we were outside and working a lot this weekend, and I was breathing a lot of dust and other stuff, and it was has me a little congested anyway, as you might be able to tell. Okay, the second type of waves, whereas the first wave was P waves, these are your S waves. S could you think of as secondary or second fastest waves, secondary waves, wherever that is. Okay, there it is. Or these are transverse waves, also known as shear waves. So whereas a longitudinal wave, the wave motion is in the same direction as the wave propagation, an S wave or a shear wave, the motion is perpendicular to the wave front. Now here's the example I always give, and it was one that I was fascinated with as when I was a little boy. I can remember if we were out in the yard doing something and my father or mother had a hose stretched along the ground, and as long as there's no water running through it yet, I loved to get that hose and pick it up and yank it down as hard as I could. And what did you see? You saw a little hump make its way across the yard. It would get smaller as it went, and I would try to see what I could do to make it go as far as possible. Well, those were transverse or shear waves, because the motion of my action was up and down, but the wave went down the length of the hose, perpendicular to the motion of the individual piece of the hose. Went up and down, but the wave went horizontally down the hose. Okay, that's a S wave, a shear wave, because they're perpendicular to each other. And also second fastest secondary waves. Now here's another difference within them and P waves. P waves are faster, not a lot faster, but faster. Here's the other thing. S waves do not travel through liquids, and that's the big key that tells us so much about the inner surface of the earth, the inner structure, stratified structure of the earth, because S waves cannot go through liquids. Because if you think about it, a pressure wave is going through air now. If you ever saw the old cowboy and Indian or bank robber or train robber and good guys, bad guys movies back in the West, how did they know when the train was coming? They put their ears down on the track, and you could hear the train coming farther away if you listen through the metal than if you listen through air. Okay, because pressure waves, sound waves, travel through all mediums. They travel through solids, they travel through liquids, and they travel through gases. Okay, but transverse waves like this, try doing that to a puddle of water. Go up and down just of the water, and the water just sits there. You go up and down and it just sits there. They do not travel through S waves. Secondary waves do not travel through liquids. And then finally, when a wave reaches the surface, these have been waves inside the surface of the earth, through the materials in the earth, because most of your earthquakes are deep in the earth, somewhere in the earth. Okay, these are the waves that bring that energy out. When they finally reach the surface, you'll see surface waves. They're a lot like water waves. They don't go necessarily in the direction of the wave propagation because there's nothing else to go there, so they move along the surface. Okay, they're the slowest of the three, sometimes the most pronounced of the three, but they're the slowest. Okay, they occur when either a S or a P wave reaches the surface. Now, I don't know if you've seen this before, but if you've I don't know if you've seen this or not. I've seen pictures of it, but they don't publish these that much anymore because they don't do that much more of them. But when they were doing nuclear testing and blowing up nuclear weapons, sometimes you would see on the surface of the ground the the big explosion, all that would happen. But you see on the surface of the ground just sort of do like this, waves just propagate along the surface. Those are your up and down crest and trough waves, a lot like water waves. These are surface waves, no longer moving in the direction of wave propagation, but moving along the surface. Okay? These are slowest, and they occur when they reach the surface. Okay. The top up here is a spring wave. Now, I don't know of many springs that you can hold that far out from the wall and they stay horizontal, but let's just imagine they could. And let's say that you're holding it out there, it stays horizontal, and then you suddenly push it in and pull it out. The pushing it in is called the compression, and when you pull it back out, that's called rarefaction. Well, if you just stop right there, back where you started from, this compressed part here moves down the spring. And then the rarefied part, it also follows it down the spring. Now, they haven't drawn this too well. This should be compressed right in here, just like it is here and here. Whoever the graphics person was didn't get that part right. That should be compressed just like that and that. And here's the rarefied part, like this and this and this. That is done correctly. And you see the whole thing, the compression and the rarefaction, is moving in the same direction as your particle motion. Particle motion was back and forth. The wave propagation moves in that same direction. Now, actually, sometimes you'll see when it hits the wall here, it'll turn around and echo back out in the other direction. So, indeed, it goes in both directions. Now, my hose on the ground, the transverse waves, you do up and down, a string like that, and the particle motion is up and down, but the wave propagation is horizontal. So this is a vertical particle motion and horizontal wave propagation. Okay? And that's what the hose did on the ground. And that's what fascinated me as a child, to see that wave propagate down the hose. Okay? And again, sometimes if this is a real taut knot here, it'll turn around and make its way back as well. Okay. Now, okay, I think we beat that to death. Those are your pressure waves, your P waves up here, your transverse waves or shear waves down here, secondary waves. Now, let's talk, oh man, about the Earth's internal structure, okay? We're going to get the figure that's on your page, or my page, your page 18.4, my page 461. And I think it shows up here, so let's show it. Yeah, there it is. All right. Goodness gracious. We got about a half hour more before we'll stop for lab. I'm just hoping I can make it for a half hour more, because I'm really feeling spent. Okay. Now, 3 main zones. The smallest of these zones, even though it seems pretty big to us, is the crust. Now, the crust is this part basically that is this darker color right there. It is incredibly thin, okay, but it covers the whole surface of the Earth. Now, they haven't shown the water. Like I say, the water is just almost negligible, even though some parts of the oceans we say are very, very, very deep, like miles deep. You're still not talking about a very big dip in the crust at all. So, yeah, where there's water, the crust goes down a little bit, but it's not really significant. Okay? That's the outer, very thin shell. Everything we have ever done on the surface of the Earth has been within the crust. The deepest mines that we have ever drilled are still in the crust. Okay? We say it's a thin shell. What we mean by that, only a few miles thick. Wait a minute, how many mines go down more than a mile? I don't know of any. Maybe there are some, but you don't ever get out of the crust. That's the only part we really know much about, and we don't know that much about it. Okay. Now, inside the crust is the mantle. Okay. The mantle starts right about here and goes all the way down to there. It is the biggest portion of the Earth's internal structure. Okay. From the outer core to the bottom of the crust. Now, we're going to give some names to some of these boundaries in just a minute, so hang on to that. I don't want to get ahead of the slides. Now, you get into here, and this is now the core. This is the outer core here, and by the way, that's liquid. Again, we've never been down, okay, okay, let me back off. It seems like I read somewhere that the Russians actually did keep drilling until they actually got through the crust and made it into the mantle. Okay, so I don't know why they did. Maybe to verify that indeed it was as we were saying it was, or scientists in general. I don't know why they did it. Maybe they just wanted to go deeper than we had ever gone. I don't know. But say again? Yeah, sure. Okay, that's something you've read, or I hope not experienced, but you read about it. Okay, right. That's pretty amazing. Okay, I had never heard that before. I wonder if that's actually ever happened or if that's just theoretical. That would be very interesting to find out about. So if you want to pursue that as a paper topic, that would be a fascinating one to read. Okay, that's really interesting, and maybe a little bit about the science of why that's true. That is amazing. Okay, but it is true that if you I think the hole would also have to have a certain diameter to be strong enough to do a little bitty hole. Probably wouldn't do something like that, but if it was a big enough diameter, that certainly would cause enough of a fluctuation that it could be amazing. Okay, the mantle, even though maybe a few people have made it into it, generally not. Okay, it starts somewhere inside the crust, and again, I'll name these boundaries later, and goes all the way to the outer core. Okay, now do not for a moment think that these boundaries are nice, smooth, spherical boundaries like you see here and here. They're not. They're rugged, jagged, uneven, very much unsmooth like this shows. Now, the outer core is all liquid, molten rock. The inner core is solid again. Okay? But the mantle is much, much, much thicker than the earth, than the crust. Okay? The core is the center part, is not as thick as the mantle, and certainly has a lot less material in it than the mantle, because the mantle is completely surrounding the core. Okay, so let's look first at the crust. The crust covers the entire earth. Even underneath the ocean, you have oceanic crust. Now, the oceanic crust, believe it or not, is much thinner than the continental crust is. Okay? And generally, its rock that makes it up is basaltic rock, which is a high iron content rock. We talked about this in the last chapter. The granites are the lighter color, lighter weight, lighter density, like that. The basalts are darker colors because they have more iron content and they're higher density. Basaltic rock. Okay. The continental crust, on the other hand, that covers much of the earth where the continents are, not where the oceans are, these are more generally granitic rock, which are again low iron content, low density rock down there. Now, let's hit just a few terms. As I said, we were coming up. Wait just a second. Oh, my eyes are so dry. Let me take another sip of water. I think when I go get your lab, I'm going to splash water all over my face because my eyes are almost hurting because of it. Okay. Now, in between the crust and the mantle is this, and good luck with pronunciation here. The best I can come up with is Mohorovic discontinuity. Okay, it's the mantle crust boundary, and the crust is low density, and the mantle is very high density, and that creates this discontinuity. Okay, the seismic wave velocity increases sharply when you go from crust to mantle, which to me is totally backwards, because the seismic waves, unless it's a nuclear explosion done on the surface, seismic waves are starting somewhere deep in the earth and coming out. They're not starting on the surface and going in general, okay? They're coming out. So what it seems like to me they should have said, the seismic wave velocity decreases sharply as it goes from mantle to crust. But they say it the other way, which is also true when you do have seismic waves going in a different direction. They just don't usually do that. Now, quite often they won't call this the Mohorovic or something like that, discontinuity. They'll just call it the MOHO. Okay, so if you see in your book the MOHO, that's what they're talking about. That boundary between that thin little crust and that great big old mantle. That would be it. This surface right, that line that separates the dark from the reddish. That line right there is the Mohorovic discontinuity. Okay. Now, here is sort of a gross description, but it's okay. Here we have the ocean over here. There's all the blue water. Underneath that, it's mostly underlain by the oceanic crust, which is high iron content, a thin crust compared to the continental crust, but high iron content, so it's much denser. Therefore, I do not like this illustration. And we'll see later, since this is a denser crust, it tends to go down rather than up. Okay? Generally, the oceanic crust subducts under the continental crust. It doesn't crawl up the side because it's denser. The continental crust is made more of granitic type material, which means it's lower density. Also lighter color too. And this is showing on a scale. This is denser, equal volume would weigh more. Okay, so there's your crust. This would be the MOHO. See, it's very irregular, has peaks and valleys and discontinuities in it. That's the MOHO, the boundary between the mantle and whichever of the crusts that you have. The continental crust or the oceanic crust. Okay. Sorry. Now my eyes have started watering. I guess I rubbed them too much. All right. Let's move on. Any questions so far? There's the crust. Let's move to the mantle. I've already been going back and forth there. It is a very, very thick shell between the crust and the core. Takes up to 80% of the Earth's volume is that mantle. It's huge. However, 80% of the Earth's volume, but only 2/3 of the Earth's mass. The Earth's mass is about 67. I mean, the mass of the mantle is about 67% of the Earth's mass. So it's 80% of the volume, but 67% of the mass. It's composed mainly of olivine, which, if you remember, was a ferromagnesian silicate. It was one of the heavier ones. Remember, there was olivines, goodness, I'm going blank on the others. Biotite was the lightest one, but still heavier than just about anything else you find on the surface. Goodness, I know the other names and they're just not coming to me. But if you go back a few pages into the last chapter, you'll see actually an illustration with several of those on it. I'm having trouble remembering exactly, but there's about 4 different ones. Olivine was the densest, pretty much, of those that were listed. Okay. It's a ferromagnesium silicate, ferro meaning high iron content, with some magnesium, but silicates, they're all silicates. Remember, just about everything on the surface, 92% of the Earth's surface material are silicates. Some of them ferromagnesium, some of them non-ferromagnesium. Okay, now, again, we've never been into the mantle. Maybe the Russians barely got to it, but basically no one's been there to study it and do much with it. How do we know how thick it is and what it's made up of and how much of the mass and volume? Well, seismological data, we haven't said how, but that tells us a lot of information about the mantle. Now, this one seems ludicrous to me, but I understand what they're saying. The nature of meteorites. Wait a minute. Meteorites are things that fall out of the atmosphere, out of the space, into our atmosphere and make their way to Earth. How does that tell us much about the mantle of the Earth? Well, the thought is the same thing that makes up the mantle of the Earth made those meteorites. That's the assumption. And guess what? It seems to hold. They have used that as the basis for their modeling and expectations of the Earth materials, and it sure works out well. Now, the other data source is when you have volcanoes which are coming from deep in the Earth, that material that's coming out basically is liquefied mantle material. So that's how we know that. Now, if you remember, we've already mentioned it a time or two, basalts are the high iron content, low, very finely grained rocks that you, here's Don. Looks like he must have had to leave and come back, or got kicked out, or his system failed or something, but he's coming back, so I already got him in. Okay. So anyway, those are your basalts. They're close to the silicate compositions of the stony meteorites. I would have thought that should be the iron meteorites, but they're really closer to the silicate composition of the stony meteorites. They are the most common volcanic rock, and that's why the base of the ocean is made up mostly of basalts, because it was laid there by volcanic activity, most of it. I would say most of the islands of the Pacifics are, if you did sorry, I can hardly talk. Let me get another swig of something here. That's the last of that one. I hope I won't need any more. Um, remember when we were talking about it, when magma reaches the surface, you change its name to lava. Same material, but you just call it lava. When it reaches the surface and cools rapidly, you get the very fine particle sizes. That's what basalt is. That's why they say it's the most common volcanic rock, because it formed at or near the surface, either underwater or on land in air, but that's what forms basalt. And for some reason, that seems to be close in silicate composition to the chemical composition of the stony meteorites. So that's where the nature of meteorites suddenly and strangely relates to how the Earth is put together interior. Okay. Now I can't advance until I can find my cursor. Come on, there you are. Click, and now I can advance. So let's move to the core. No, we're never going to get close to the core. Okay? Makes up about 15% of the Earth's volume. Now, what volume was the mantle? 80%. Okay? The core, 15%. So it's much smaller volume than the mantle. What would that leave the crust as being? 80% is the mantle, 15% is the core. This is the volume. 80 and 15 would be 95, so 5%, yeah, absolutely, 5% of the volume of the Earth is made up of the crust. And you think that's a pretty small percent. Okay, it's covering the whole surface, so it has to be awfully thin. But look at this one. The core makes up about a third of the Earth's mass. Only 15% of its volume, but a third of its mass. That's 33%. So that means it's close to twice as, maybe more than twice as dense as most of the other Earth materials. So it's really, really dense. How much does that leave for the crust to be? 1/3 of the core is 1/3 of the Earth's mass. The mantle is 2/3 of the Earth's mass. That means the crust, even though it's 5% of the Earth's volume, is negligible in mass, because the other parts are so much more massive than it is, so much heavier, so much denser. Okay, so how do we know all this? Well, here, and this is pretty fascinating what they've been able to put together. They have studied P-wave seismological data. Now, what do we mean by that? Those are your primary waves, your pressure waves, your waves that go through solids, liquids, gases, everything. Those are your P waves. They're the fastest ones. They've studied that seismological data, and here's the amazing thing they found about it. Now remember, I kind of hinted at this before. I'll say it again now and probably repeat it other times. Scientists in general have done far better than politicians and just about anybody else as far as international cooperation. And we've already talked briefly about two things. One is seismologic data. The seismographs are placed all over the surface of the Earth. In countries that won't even talk with each other otherwise, the scientists talk. The scientists communicate. The scientists set these up so that everybody sees what everybody is measuring. Okay? It is so positively beneficial for everyone that there's no competition to speak of. There's no it's just more cooperation than competition. I'll put it that way. Okay, that's one. The second of these is tsunami data. Everyone who bounds an ocean, some countries are completely landlocked, but every country which has um, oceanic water associated with it as part of its boundary, they all participate in tsunami data. All the tsunami uh, equipment is tied together and read together, and you can tell what's happening. Otherwise, the data wouldn't be worth much if you couldn't compare it with all of them. So let's get this seismologic data that we've studied. Everybody has it and can do it. Okay, let's say that an earthquake occurs somewhere on the globe, anywhere you want to choose on the globe. It could be deep, it could be moderately deep, it could be shallow, but somewhere on the earth, somewhere in its interior, you have an earthquake. Okay, the P waves will go all the way through the earth, and here is the earthquake right here, wherever it happens to be. It's not necessarily at the North Pole or anything like this. Wherever it is, turn the earth so it's on top. Okay, and these are the primary waves. They go here and here and here. Now, why do they bend like this? Because of variations in the density of your materials. Somewhere here in the very end here is a Moverovicic. That is a distinctly different boundary than the crust. Is very low density compared to the mantle. Okay, so you'll have a very much of a bending of the material there. But it only goes so far. Those P waves will only go to about 103 degrees from the point of the surface of the earthquake, and 103 degrees all the way around that globe. Okay, 120. And then you have what they call a P wave shadow zone. In other words, there's no P waves detected anywhere here relative to that earthquake. Okay? Now, you keep going around the globe, expecting never to see another P wave from that earthquake, but sure enough you do. On the other side of the earth, you get more P waves. Okay, and you know they're P waves. You can tell by the characteristic. They're P wave, primary waves, pressure waves. What is that telling you? Well, as we said, pressure differences and density differences make these things bend and curve like this. But when we hit the boundary, so to speak, between the mantle out here and the core in here, sorry, I've got to get something else to drink. I'm so sorry. My throat's giving me big problems now. We lost the slide. These waves go out here and bend. But when you go from solid mantle to liquid core, remember the outer part of the Earth's core is liquid, molten material. You have a big, you talk about a boundary here, that is quite a boundary. You have a lot of what they call refraction, bending of the waves here, and that bending, and then you get near the inner part of the core, and it's solid again, and you have even more bending, and then you go back through the less dense liquid here, and it's bending in the opposite direction. That's what creates the shadow zone. So basically, it's the boundary of the core between the mantle and the outer core that gives you this shadow zone. So they've measured it, earthquake after earthquake after earthquake, no matter where on the globe it is, for 103 degrees pretty much you measure those primary waves. Then you have a shadow zone between 103 and 142, and you pick up on the other side of that and measure all the way around. Okay, that's because of this the characteristics of that outer core right there. Okay, that's what creates that shadow zone. Okay, now, but you do pick up P waves again here at 142 degrees all the way to 180 from the point of the the propagation of the waves. Okay, now, so that enables the scientist to estimate the shape, approximate shape, and the size of that outer core, the outer part of that. Now, believe it or not, the data in here actually gives them a lot of information about the size and shape of the inner core, the solid core, because that's what's creating this compression of waves here that then decompress here and here. Okay, so indeed there's more to it than that, but that tells us the makeup of the interior portion of the core, okay, which nothing else is going to be able to do. So the size and shape of the outer core, but also information about the size, shape, and composition of the inner core as well, to estimate that, what makes it bend like that. Now, let's continue with the core. You also have S wave, secondary wave, shear wave, seismic data. When you have that, look at what you get. There is absolutely, now notice shear waves, remember, they are the ones that go perpendicular to the propagation of the wave. Well, guess what? They don't go through liquids. Therefore, you get nothing on the other side of the core. So this tells us that outer core, the size and the shape of it, we're told by the P waves, but the fact that nothing makes it through of the transverse waves tells you that outer core has to be liquid. Okay, if it weren't, some of those S waves would make the way through. They do not. So your shadow zone here are from 103 degrees to 103 degrees. No direct S waves are received anywhere outside that cone, you might say. Okay, so the core acts like a liquid, not allowing S wave propagation. Now, the core has two parts, the liquid outer core, the solid inner core. That's supported by the S and P wave data. S wave can't tell you much except that the outer core is liquid. But if you go back to the P wave data, and this contraction in here and expanding back out here, I can't get the cursor to come up. There you are. How they join together and then spread back out as you go, that's basically based on what the inner core's characteristics are. Much denser, much probably hotter, and that type of thing. Okay. All right. I think we beat that to death. Any questions on that? Oh my goodness. Valerie, were you going to let me go over? All right. I think we are at the place where we have to stop today because we want to have a full 2 hours on the lab, because last time we did not. And let me get what the next slide is so I'll know where we begin. Other core evidence. All right. So this, basically is somewhere around page 463 or your page 18-6. That's where we'll be beginning next time. So let me go on and I'm going to stop the sharing of this for right now, and probably shouldn't have done that in that order. Let me see if I can get my, yeah. Okay. Go in that one. I don't think I need that any longer. Okay. Now I think what I'll do, since I said we were going to do this anyway, I think I'll do it now. It's going to take me just a moment. Probably, can you still hear me on Zoom? I know you probably can't see what I'm doing. Can you hear me?
Yes, sir.
You can. Okay, good. What I'm going to do is get to Blackboard. And it's just going to take me a little bit to get there because I have to go through so many steps to do so. Okay, getting closer. Okay, something's messed up. My finger must have hit a bad key. Okay, it's a little bit closer. Okay, I'm going to go in. All right. I think I'll go back to Zoom, go back to the meeting, and share the screen. I think this is the one I want. Yes, can you see my Blackboard?
Yes.
Okay, good. So this is for, I can't remember, was it Jacob, I think, was asking about this. Whoever it was, here's what we do now. Here are my courses. There's my Physical Science 111 Summer. Click on that. And then when you get on this, do you see this icon up here that looks like an envelope? You see it? That's messages. Okay, are you with me, Jacob, or whoever was asking? Do you see that in Blackboard? The messages? Okay, click on messages, and there you'll see. Now, Scott and Valerie have sent me something lately since the last time I looked. Yeah, just an hour ago or 7 hours ago. Okay, I had checked on this before we went out of town this weekend. But after that, you won't see that. I will. Okay, after that, here's was the third test. There was the second test. There's the second lab. Scroll on down. There's the third lab. There's the first test. And there's the first lab. Okay, so there's all your labs, all your tests so far. Now what I'm going to do is let's do a quick break. We're in between class and lab. I've got to run downstairs and take a picture with the iPad of your lab, and then I'll be coming back. I'll have to send it to myself through an email. I'll come back up. I have to process it a little bit to get it into a form, and then I'll load this on Blackboard right here. So if y'all need to take a little break, take one. I'm going to pause the recording right now to get to it. First I have to go to my email, and I didn't know I'd lost my email, but I have, so let me go back to email. Sorry, I think I'd be having to do this because I had it up before class. I thought I still had it up. So here we go. This isn't very exciting to watch, but Okay, is someone saying something to me? Okay. I guess I should ask, can you hear what I'm saying, or have I disconnected? All right. Okay. Okay, it's very slowly happening, but it is happening. Here is the file, I hope. See how it looks. Not as good as I hoped it would. Let me expand the thing here. Okay, that's better. Not great, but still better. Well, how do I get the pages to turn? Page 1, page 2, page 3, page 4, and page 5. Okay, that's going to be the lab. What I want to do now is, okay, is someone talking to me? Oh, screen sharing is paused.
It's from at TV.
Okay, so that's just, I didn't know, I think this is me. Nope, that's not it. That's it. Okay, that's what the lab is going to look like. I think what I have to do now is download it. If anyone can think of a better way to do this, I'll be glad to do it. Okay, and then I'll pull this up and hopefully save it as, okay, one, I think it was already here, weren't you? I believe he was. Yeah, one was already here. Okay. My screen sharing is paused. Let's get back to, this is it again. Okay. I probably didn't want to do that. Okay. I need to get, yuck. Let's see if I can just save as here. Nope. I can't retrieve it again. Okay, I'm going to download it again. There it is. Okay, this is what I want to save as. Let's see if this will work. Okay. I think I'm in the right file, but this thing is blocking my seeing it. So I'm going to, there we go. Yep, I'm in the right place. Okay. PHS111 lab. What is this? Lab 4, isn't it? Okay. Okay. Now that that's done, I hope I won't need these again, but if so, I'll go get them. Okay. Now let's do here. Okay, I'm in the right place. I think it's the right one. Yeah. Okay. Sorry this is so slow. I need to do a new one, but I can't see it. Here we go. There it is. There's the ad. And Jacob, you're in the way again. Yeah, I guess you realize that. So I'm going to move you out of the way. Okay. I'll send it to everybody and attach it. And of course, I don't know why it does this. It always sends me to the wrong folder. Lab 4, that's the one I just did today. Okay. And, oh, Roy, you're in the way again. There you go. All right, there we go. All right. Now, all of you should be getting it fairly soon. Okay. I'm going to try to figure out where to best put y'all. And I want to pull this up. Now, let's see if I can rotate. There we go. First time. Okay, and of course, Valerie's in the way again. Okay, let's get Valerie out of the way. Okay, here we go. Here's today's lab. Can you see it? Experiment 42, properties of common minerals. Everybody? Yay or nay? You can? Okay, good. All right. We're going to be talking about minerals today. This is the first part of chapter 17, which are naturally occurring. We went over that. Inorganic, solid elements or chemical compounds with crystalline structure. Those are requirements of a mineral. Okay? They say about 25,000 different minerals are known to exist. Only about 20 are common in the crust, and they mention a few of those. Now, we don't have, well, I do have sort of a mineral collection on campus, but we can't use that. So what we're going to be doing is not what they're saying here, but we're going to look at the same things. Here's what we're going to do, and I'm going to pull up what they call the whiteboard. I need y'all to get this information down, okay? I'm going to sort of type it in. Here is where you're to go, okay? It's a website. And the title of it is Web Mineral. And hold on just a minute. Yuck. There's two websites that are almost the same name but slightly different. This is Web Mineral with no S. Okay, now wait, let me back up just to make sure everybody. This is http://webmineral.com. Okay, and then if you want to, you're going to do another /data, and then you could do the next slash if you wanted to. It's up to you. I would say it's probably quicker to go on and do that. Sorry, I'm dropping things all over the floor. The first mineral you're going to look for is entitled calcite. C-A-L-C-I-T-E. I just messed up. Yuck. I'm having trouble. Huh. I just had it in my hand. I'll put it back in the stack where it doesn't need to go. I'll get okay in a minute. Yeah. And if you want to, you can type in after that calcite. That just saves you a little bit of lookings. Let me expand my thing here. Okay, that's where you're going to go. Don't go there yet, but that's where you're going to go. Okay, the HTTP ://webmineral without an S, webmineral.com/data/calcite. Okay, now let me tell you what you're going to do first, then we'll come back and actually go to that site. Okay, so let's go back to what I was just sharing before. I believe it was this one. Yeah, there it is. Okay, so you'll go there and you're going to develop a table of mineral properties. And here are the properties you're going to look at. The first of these is color. And remember, color is the most obvious thing about a mineral, but it's one of the least useful in classifying a mineral. Okay, we're listing these mineral properties, but if you just use color, you're kind of lost. Okay, so when you go to this website, you're going to see a whole list of colors. Just write down a few, okay, 2 or 3, something like that, just till you fill your box, and then go on to the next. Now, something that's far more useful in classifying minerals is streak. That's if you take that mineral and move it over something that is an abrasive material like sandpaper or corundum or something like that, you'll leave a little streak. That color is way more indicative of what your mineral is. So you'll look for in the thing streak, color, then streak. Okay, then hardness. And remember the Mohs hardness scale? And you can either just put the hardness number down or you can put the identifier with it. Okay, and you'll see in the table it usually uses either this, that, or something else like fingernail, nail, copper penny, pocket knife, something like that. Whatever they put down, you can put down. Okay, so that's going to be the third column, I believe. It may not be according to columns. Let me get the lab in front of me. First column is column, then the luster. We haven't gotten to luster yet. Then streak. And then the fourth column will be hardness. That's where Mohs scale goes. And then we'll go on from there. Okay. So that's Mohs scale. This will be on your second page. Fourth column, hardness. Okay. Then, now this one you put together on the table. Cleavage/fracture. That's how it's listed in the table. Now what cleavage means is the cleavage is a tendency of a mineral to break along smooth planes. The cleavage occurs in parallel planes in some minerals and one or more direction in other minerals. Okay? Sometimes the cleavage is perfect. Other minerals may have indistinct cleavage. So you'll pick out whatever they tell you about the cleavage and put down a few words. They may have numbers. That's one way to represent them. You may not understand what the numbers stand for, but use the numbers. Okay, it'll either be perfect or it'll be indistinct, something like that. Then you have a slash in your table, and it says fracture. Fracture, minerals that do not have cleavage may show fracture. So if it shows cleavage, list a thing about cleavage. If it doesn't show cleavage, list a thing about fracture. Okay, now that may be irregular broken surfaces. It may be a distinct way of fracturing, like a conchoidal fracture. There's your obsidian again. Who was it? Harry or whoever. So you'll list whatever they give you in the table. We'll see this. Then back on page 1, the second column after color was luster. Luster describes how the surface sheen, that's the way the mineral reflects light, and some will be metallic, some will be pearly, vitreous like glass, glossy, dull. There's a whole variety of names. You'll see these at the website. Now, on your lab, the very last column says other. You're not going to just put down other there, you put down density there. Density is probably the very best indicator of what mineral you're dealing with. Okay, so that's going to be your last column. It says other, you put density there. That's going to be your last column. Okay, now when you finish everything on the lab, don't forget to come back and answer this question. Was the purpose of this lab accomplished? And why or why not? Only need a word or two for this one and maybe a sentence or two for that one. Okay, that's all. Okay, but here is your data table. Now this is what I was talking about. The very first thing you'll see, and that first mineral will be calcite. The first thing it's asking for is color. Okay, and again for calcite you'll probably see 2 or 3 or 5 or 7 colors. Just list what you can in this column without getting too crowded. The top however many. Then luster. Okay, what was mentioned earlier was streak next. You do luster next. That's going to be pearly, vitreous, metallic, some sort of word like that. Then streak, and again this will be a color, but it'll be the color of the streak, not the color that you see in the mineral. Okay, now I'll come back to something later. Let's go to the next page. Okay, the next feature will be hardness. Okay, and that's what you put here. And there you can either just list the number, you can list the classifier, the relator, the mineral, whatever you want to put there. I'd say what's on the website. And then this one, like I said, is cleavage/fracture. You'll either say something about cleavage or something about fracture, or maybe a little bit of both. Okay, and then the other, mark through other, and you write density up here, density, or specific gravity. Either one of those will work, density or specific gravity, and that's what you'll put in this column. That's the very best property for classifying a mineral. Okay, now the same minerals you see here were on the previous page, so I'm just going to address these. Okay, now I know beyond the shadow of a doubt that calcite will be found in that website. Probably magnetite as well, probably pyrite, believe hematite, limonite I think, but I'm not certain, quartz for sure, fluorite I'm pretty sure, apatite for sure, feldspar I'm pretty sure will not be listed as a mineral. Feldspar is more of a, I'd say it's more of a rock or a class of minerals, you might say. If you can't find feldspar or any of these others, like maybe limonite or some of these others, bauxite, if you can't find them in that website that I told you about, then go out and do a Google search or some sort of search, typing in this name, and you're going to be given a whole host of minerals. While you see one of those minerals, go back to your website, keep it up there, go back to your website and see if you can find that mineral. If you can, then instead of feldspar right above here, write in the name of the mineral, or type it in, however you want to do this. Type in the name of the actual mineral that is a feldspar. Same thing may be true of hornblende. No, hornblende was one of those iron ones I was trying to think of before. Bauxite is basically aluminum ore. Okay, you'll probably have to find another mineral that is a bauxite. I believe goethite or one of those might be. Okay, I think most of the rest of these are listed. Okay, but anyway, you should be able to. So if you can't find the specific name here, go to a search, get a mineral name, go back to your website, see if you can find that mineral name, and then type it in if you can, and then list all those characteristics for that one. Okay, does that make sense? Okay, let's actually go to the website. Okay, now I've got to get there somehow, and I think here's how I'll do it. Oh, here's how I'll do it. Just do the plus here and do HTTP colon slash slash WEBMINERAL. Okay, what was it? Webmineral.com. That's what I thought. I thought there wasn't anything else there. Okay, y'all can be going to the same place too. And I think it just speeds it up a little if you put slash data slash and just start with calcite because that's the first one. CALCITE. That saves you a bunch of looking. Okay, hit enter. Takes a while to get there. New tab. And we have pretty slow internet here, so you may be there already. Well, it's really slow today. Can you see what I'm doing on, it says the screen sharing is happening. Can you see it okay? Say again? Yeah, it's on Google, and I've typed in webmineral.com slash data slash calcite. That just gets us started. But I'm waiting, it says new tab, and it's just waiting for it to come up. I don't know what's taking it so long. What's that? Yeah, it may be. So if you're using another search engine, you might be there faster, or another, yeah. Are you already there? Okay. It may be our slow internet because I know I'm pretty sure my wife's is probably on the internet too, so we're um, maybe packed out here. I don't know why it's this slow though. Most of the time it's not. So what I'm going to do after a while, I may try this again. Let me probably should have stopped the last one, but oh, here we go. Okay. I have a feeling that Kermisha's in the way again, so I'm going to have to move you to the other side of the page. Okay. They say this is a non-secure website, so whatever that means, you're okay. Are you already past this one, resolving host? Okay. You've already gone past A to Z, right? Okay. My guess is the next thing we're going to go to is properties, but I don't know that for sure. I'm waiting for A to Z to finish resolving host, whatever that is. The internet has been going much faster today until just now. And maybe I've got too many things open. I don't know. Because I have Screencast-O-Matic, I have Zoom, I've still got Blackboard open. I should ought to close that. I don't know if any of these are super big drains, but they're not doing anything with them. But I've still got them open. There we go. All right. Now, right now, it's looking like it didn't pay any attention to me of what I was asking it to do, like find calcite. So I think what I have to do is go to the C index here for calcite. Okay. They changed this slightly from term to term, so I can't say that everything. It's still waiting. Goodness, this is the slowest I've ever seen it, I think. Well, maybe not ever, but okay, anytime now. Resolving host still. I don't know. I don't guess it would be the fact that all of us are on it at the same time. No, I don't think that's ever been an issue, because most of the time they do it together. Is everybody sort of doing this with us now, or are you just spectating? I guess if you're looking at your computer, you can't be doing it, can you? So I'm recording this just so everyone can see it. Hopefully it won't take them as long as it's taking me. Okay, there we go. Now what we do is go down here till we find calcite. C-A-L-C-I-T-E. See, they said 25,000 or something like that. Oh, there it is. I almost missed it. There's calcite. Does everybody see it? Okay. And if you recall, I said it was calcium carbonate. You don't need to know that. Anyway, I'm going to click on that, calcite. Okay. Now it talks about chemical formula, pronunciation, all this kind of stuff. That's not really what we want, nor do we want image, though they're pretty. Well worth a look. The ones I got from the kid, that guy that was a miner, looked a lot like this. I mean, they're just absolutely beautiful. They're very clear. The picture's a little fuzzy, but you keep on going. The calcite crystallography, we really don't care about that. I did crystallography stuff when I was in master's. Here we go. Physical properties of calcite. Do you see that? And there they are. The first one that was asked for was color, and there they list 5. If you can list all 5, list them all. Otherwise, just do maybe colorless, white, whatever you can get on that block. Okay? The second column said luster. There's luster near the bottom. It's vitreous or glassy, and if you ever saw that mineral, you would know it looks just like glass. Okay? The third column was streak. There's streak, a white streak, even though it may have been a colorless or a pink or a yellow or brown mineral looking. When you did the streak, it came out white. Okay, the next one was hardness. There's your hardness. Number 3, calcite. If that's what you want to put, you can certainly do it. Okay, it's its own classification. Okay, everybody measures number 3 by calcite, so you're perfectly fine to do that. The next column was fracture slash cleavage, or cleavage slash fracture. It's perfect, and you can put these numbers down if you want to. 1011 perfect. You don't have to put them 3 times. But then fracture, it is brittle, and when it does break, it's concordial. Okay, now if you can't put everything in, just put 1011 perfect, and then slash, because it's cleavage slash fracture. On the fracture part, after you slash, put brittle concordial. That's enough. If you can't get it all on there, abbreviate or something. Okay, and what was the 6th column? Density. And there it is. Actually, that is specific gravity. So either specific gravity or density. The reason I know this is specific gravity, it has no units. Density will always have a unit. It'll either be grams per cubic centimeter, kilograms per cubic meter, pounds per cubic inch, or if it's a specific gravity, it'll just be this. So that's actually the best number. Specific gravity, no units, 2.71. You've just done calcite. Okay? And then after that, you go to the next mineral. And see what it is. Magnetite. So you just keep going like that. Okay? Now, do you have any questions? This is basically the only group that you'll need. You just have to keep scrolling down till you find physical properties of whatever the mineral is and go. Now, you see you're not using a lot of these, like whatever diaphanity is. You're not using it, so don't pay any attention to it. Luminescence you're not using. Just the 6 that you're using. Color, streak, no, luster, streak, hardness, cleavage slash fracture, it's actually 2 of those, and then density. Now, all the minerals won't be listed in the same order, so you have to sort out the order, and occasionally you might find one that doesn't have anything listed, so that's okay to do too. Now let me go to one of those problem children. Okay, I'm pretty sure feldspar would be a problem child, so let's go back and see if we can find feldspar. So I'll go back to A to Z. I hope it won't take as long as it did the first time. Yuck, it looks like it's going to. Yuck. There we go. See what happens if we go to feldspar. Okay, now you have to scroll down, oops, feld. Okay, get the correct spelling. F-E-L-D-S-P-A-R. F-E-L-D. Not there, right? Did someone just come in? Okay, not there. So what do you do in that case? Now, what I was looking for was a shortcut to Google that's not going to really mess up everything. Okay, I think I'll just have to do it this way. Okay, here on the line of Google, I'll put, or whatever search engine you're using, F-E-L-D-S-P-A-R. Okay, we'll do a search. New tab is waiting. I was hoping it wasn't going to take so long. I don't know, is there any difference in typing up there and typing down here? Should I have done the Google search here? I didn't think it would. Okay, I thought if one was a little faster, I want to go with the fast one, because most of the time I do that and something pops up within just a few seconds. I don't know why it's so slow today. Here we go. Feldspar. Feldspars are a group of rock forming, oh wait, here's Capri is coming back in. She's already been here today. Okay. They crystallize, blah, 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 blah. Notice all these words: intrusive and extrusive, igneous rocks, blah, blah, blah. Also present in many types of metamorphic rock. Okay, so far I'm not seeing, that's not a word, that's not what you're looking for. Let's just see. Remember when we say crystal system, triclinic or monoclinic, we're not looking for that today, but you have some good pictures of it, but we still don't have a name. So let's see. In fact, let's see, is there enough information right here? There's color, there's streak. I don't see luster or what? Or hardness. Okay, so it's probably can't just use this. Okay, yeah. Let's see. Didn't know they made up. Okay. See, this is a group of minerals. That's why you can't find anything. Okay. Um, let's see which of these might be the best to look at. Let's just try this one. I think this, you decide, for yourself. Let's just see if this one will work. Seems like that might have the most information of the ones I see here. Maybe properties, uses, types, but this seems like good. Mineral information. Still waiting. It usually goes faster than this. Of course, most of the time we're on campus. Okay, there's a feldspar group. Here are a few. Amazonite, albite, and whatever that one is. So that's three. I would say I've heard of albite probably more than the others. So let's see what else they show here. Of course, Scott is in the way here, so I'm going to have to move him to the other side. Okay. Let's see. Now I can get to my arrow. This doesn't look all that useful. Here we go. Here's a whole bunch of them. Here they are, group numbers. Albite was listed, well, it's alphabetical. So I would go back to your listing here, A to Z, and go back up and try A to Z here. Let's see if albite will work. That was much faster. But now, of course, Jacob's in the way again, so let me move him out of the way. Okay. So I'm just showing you how you go about doing this. You can do it much faster than I can, I bet. You're better at it than I am. Albite, there it is right there. So on your sheet of paper, well, let's just take a look at it first. Oh, that came up quickly, didn't it? Okay. Here's albite information, images. That looks a lot like what we were seeing before. Crystallography, that's... here we go. Physical properties. Here we go. Yep. So I would put on, if you choose to do albite, You don't have to. Under feldspar, right above there, write albite. And then you give the color, some of the colors, some of the luster. It's only one. Some of the streak is only one. The hardness, right there. There it is. The cleavage slash fracture. You might put both of those if you want to, or only one. Fracture, uneven, blah, blah, blah. Okay. Then the last column, remember, is density. Now this one, you can either put the range or put the average or put them both. But that last column is going to be density. And since albite is a group of minerals, some of them might be denser or less dense than others. Okay. Do you see how to do it? Most of the minerals you'll be able to get right off of this table. Those that you can't, then do something like a search and type in the search. Keep digging until you find the name of a mineral. Go back, see if you can find it here. If you can, write that name in and then put its information. Does this make sense?
Yes, sir.
Okay. Do you need to get off the air so you can get on it and start doing it? Or what you want? I can stay on and help you out if you get hung up, or you can can't help you if you get hung over. No, never mind, that's beside the point. Just let me know what you want to do. Work on your own, or you want me to hang on for a while until you feel more confident about it.
I think I can work on my own.
Okay? Everybody else feeling about the same?
I'm okay to work on my own as well.
Okay. Okay. Anyone want me to stay on? I'll be glad to if you need me to. No more of that. Y'all can move much faster than I can. Say again?
Can we recreate the chart if we want to?
What do you mean by that?
If I want to type it out instead of handwriting.
Oh, sure. Just be sure you get all the information included. Those 6 things, be sure you put density in for other, and be sure at the end you answer whether you thought the lab was effective or whatever it asked for. Yes.
Are we still allowed to manual our work like we did in the math class?
Absolutely. If you don't like, okay, if you'd rather mail, you certainly can. You can email, you can message, or you can mail it by snail mail. Any one will work. Certainly will. You still have my address, right?
I think I can go find it in my notes somewhere.
Okay. Do you want me to give it to you now?
Yeah, that's fine.
Okay, 4504. Do you want me to type it on that form that I was doing before?
You can say it, it's fine.
Okay, you're okay. 4504 Claremont, CLAIRMONT Avenue South. You don't have to put the South, but I usually do. Birmingham, Alabama 35222. Do you need the 4-digit suffix, or are you okay with that one?
No, I'm good. You said 405 Claremont Avenue, South
Okay, wait. 4504. 4504. Yeah.
Yes, sir.
Yeah. The rest of it you got?
Yes, sir.
All right. Any other questions? Great question. All right. So if y'all are through with me, I will go out there and also put your test 4 out on Blackboard message, because we have finished chapter 4, so I'll go on and put the 4th test out there. You okay with that? And who was asking earlier? Was it Jacob? Did you understand where to go to get this stuff? By the way, y'all didn't have me call roll again. Let me get roll again. Uh,
So,
yes,
question.
yes.
Would limonite actually be spelled with a Y after the O?
Okay, that's well. I always call limonite, but are you saying Limonye?
Never mind. I'm sorry. I was looking at the wrong one.
Oh, okay, okay, okay. And that may be one of the ones that you have to go out and do a search on. There's like three or four that you have to do that, and that may be one of them. I just don't remember year to year which ones they are. I knew feldspar.
Okay, I found it. It wasn't highlighted. It was a white on it.
Yeah, it, it was a low light. Okay, all right, all right. Now, rest of you are okay with it. I'll go out there and put your test 4 out there as well. I can't remember now if I've already got it in a form that will load, but that means I'm going to have to get off if I do that. Are there any more?
Take the roll again?
Yeah, that's what I was just going to do. Let me see if I can do it this way. That'll help some. I see Capri is here. Okay, my pen is, it does this every time. As soon as I go to take roll, it doesn't write. Okay, Capri's here. Thomas is here. Kermisha's here. David is here. Don is here. All right, let me scroll on down. Now, if you've seen anyone that was here, okay, Harry's still here. Can't shake Harry, can we? There he is, okay. All right. Jacob is still here. Juan is still here. Okay, Nakia is still here. Did I pronounce it right that time? Okay. Roy is still here.
It's Nakaya.
Nakaya, I'm so sorry. I put a long I over it, but I couldn't read it. Okay, sorry about that. Nakaya. Okay. Scott is still here. There you are. Okay. Valerie is Valerie still here? That's what a shock. Okay. Okay. I think that's all. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep, that's it. So it looks like we lost Caitlin. It seems like the only one we lost. Okay. All right for me to get off?
Go ahead.
Okay. What I may do is I may keep the Zoom up, and once I get your test out there, if it doesn't take too long, I'll come back and check on you. But yeah, okay. All right, so I may keep it up. I may have to close it down if the test has answers on it. I'll have to see. I don't want you to be able to see it, but anyway, I'll figure something out. All right. Take care. If I do, don't. If I'm not able to get back, if you have any questions, you know you always have at least a week to work on it. So ask me questions on Wednesday. Okay. All right. Okay. I'm going to stop the share for now, but I'll leave Zoom open for now. Okay. Looks like everybody's leaving, so I'm going to end the meeting, okay? Do any of you want me to keep it up? Because I see people. Okay, people are leaving like leaving, so I'll go on and end it. Catch you on Wednesday then.